Good evening, it's 5 o'clock and we're gonna start, inshallah. The first thing I wanna do is to show you some updates. So I'm sharing my screen, and if we go to e-learning, did you notice any new thing posted today?
الكالندر عشان الباكجز.
Yes, great. By the way, don't forget to write your ID and name in the chat. I added a few things actually. The first thing, I do things step by step. Last time after the class, I added the slides and the recording. I showed you some stuff here. I added some manuals, data sheets that we're going to use. Today, I added this link, a link for you to download a software package. Okay, so you download it. You download this software package. I'm going to tell you what is it about. Okay, those who are coming late and are disturbing, honestly. I have to. So guys, please try to come on time at 5 o'clock sharp. When you come late, you disturb me, I may forget you or you distract me. Okay, guys, so I was talking that I have added this link to download something called Codewarrior IDE version 5.1 special edition. You download it from here. What is this? This is the IDE we're going to use. It is by Freescale that we're going to use to program the microcontroller, the HCS12 Freescale microcontroller. Okay. So yeah, and you may not use it by, I don't know, within a month maybe, but have it ready on your computer. Okay. Take your time, download it. Make sure to install all needed drivers. When you put a USB, make sure that you get a COM port number and you do the setup, install it. It's there now. And I'll show you around how we will use it. We will use it together when it's time, but for now it's here and you can download it. Again, I'm going to repeat a second time. Those who come late distract us. Please don't come late. Please come at 5 o'clock sharp. Okay, so Codewarrior, this is the IDE that we're going to use to write code in C and assembly to program the HCS12 microcontroller. It is called Codewarrior by Freescale. Then here's a note by Engineer Ragad. She put it for you there. About the packages you're going to pick. You're going to pick a package that includes an HCS12 microcontroller and an Arduino board with their accessories, everything to make them work. You pick those from Engineer Mahmoud Faris. Here is his email, okay? He is located at the projects lab, first floor, School of Engineering. To go to the university, you need a permit to get in, okay? So you need to to email Mahmoud and tell him that you are gonna come on this day from 9 to 2 or whatever, and he will send you through email a permit to get in, okay? These are his available, our people work remotely some days, and other days they come physical to campus. These are his physical days on campus, okay? So try to find a date, Sunday, these Sundays, these Tuesdays, these Thursdays, for the coming month. If it doesn't work with you, you email him, okay? And find a slot. And when you email him, you can copy me, copy me and copy engineer Ragad. Okay. Me and Ragad. Both of our emails are here. Mashi. And he'll be helpful. I'm sorry, I have to pause for a second. Do I have to? It's related to the, 1 second. How do I, okay. You know what, just ignore it. طيب. So this is about the boards, okay? You have the full month to get it. When you get the board, you have the IDE to start programming it. We're going to use it together. Don't worry. You just get it now. Anything else I added since last time? I added the recording of the last lecture and the topics we did cover over that time. And let's move on. So last time, if you remember, we talked about computer systems, embedded computers. We just started the first chapter. We talked about general concepts, reminding you guys about what is random access memory, what does random access mean, what is how is memory RAM different than ROM, what is E2PROM, what is flash, what is access time, how to design a RAM connected to the CPU or the processor through its system bus, control, address, and data buses. Okay. And we got to a point where we are gonna talk about, so really, we were here, we covered okay, and this has to happen every time. Duplicate. Okay, so we start, we spent a lot of time here. We talked mainly here. You need to remember that we have a program memory that is non-volatile, usually flash memory in microcontrollers to put our program at, and data memory, which is usually two types: E2PROM for non-volatile memory for data, permanent data, and SRAM for that is volatile and for temporary data. We mentioned I/O. We're gonna come here. We almost have a separate chapter for each peripheral, input output. We talked about the buses. Today we're gonna spend some time here at the processor. We're gonna talk about the control unit. We're gonna talk about the ALU, and we're gonna talk about the register. 3 things here. Okay, so what we start with the processor, the ALU. The first thing is the ALU. ALU stands for Arithmetic Logic Unit. This is a very simple ALU, just to give you the understanding of the basic idea how an ALU works. First, you need to know that there is code placed in the program memory. Okay. And the control unit fetches this code. We're going to talk about the control unit. It fetches the code, brings it to the processor, decodes it, okay, and executes it. When it executes the code, it sends it to the ALU, the Arithmetic Logic Unit, to perform an operation on the operands that are part of that instruction. So the opcode tells the processor what to do on the operands. So add, for example, like the add over here, sorry. So the add here, it says add number 1 with number 2. The machine code, the opcode for the add is 0, 0. Number 1 is A, number 2 is B, okay? And these are fetched from the place they are. They could be in registers inside the processor. They can be in the program memory part of the opcode. They can be in the data memory. Who decides what signals to send, what bits to take to this line, what to send to the other line, the control unit, after decoding the instruction. This is a simple ALU that can perform 4 operations, just to give you an idea how an ALU works. 4 operations: add, subtract, and OR. Basically, it is a multiplexer. You know what a multiplexer is, right? A multiplexer has select lines that select the input lines, and which of the input lines goes to the output, okay? So this is a 2 by 4, a 4-to-1 multiplexer. So 4 inputs. To be able to select among 4 inputs, you need 2 select lines, right? You need select line 1, select line 2, 0, 0, 0, 1, 1, 0, 1, 1, right? So if you say 0, 0, you're selecting the first input. If you say 0, 1, you're selecting the second input, the third input, the fourth input, okay? 0 to 3. So whenever we have a machine code, opcode, that is 0, 0, it comes to this select line. That means whatever is on at this input of the multiplexer will pass out to the result, okay? It will be connected to the result. It is going to be the result. So when we put a 0, 0 here, this is going to be the result, and add a sum. The sum comes from an adder. This is a full adder. If you remember logic, a full adder adds 2 bits with a coming in carry, right? So if this is 0, 0, the output of this adder is passed as a result, which is the sum. The input to the adder first is x, and y and x. X is a, okay, a. So you have a here. Then what is b? What is y? Y is something that comes from another multiplexer, a 2-to-1 multiplexer. So if there is a 0 on the select line, the multiplexer will pass b, right? Pass b. If there is a 1 on the select line, the multiplexer will pass b inverted. B inverted is the first complement of b, the 1's complement of b, right? Okay, where does this select line come from? From this comparator. A comparator over here compares 0, 1 to the opcode. Okay, if they match, you get a 1. If they don't match, you get a 0. طيب, our opcode is 0, 0, 0, 0. Does it match 0, 1? No. So you get a 0 here. A 0 will cause B to pass through this multiplexer. Okay. So, and if there is a carry in from a previous stage, it's added to this full adder. So A plus B will pass here to the sum and pass to the result. So if I put a 0, 0 here, the result is adding A and B. طيب, what if we have a subtract? طيب, how to change the color? طيب, subtract. Subtract is in green. If I put a 0, 1 here, 0, 1, that means whatever on the 0, 1 input is going to pass out to the result. What is on the 0, 1 input? It is the sum again, or the output of this adder. طيب. However, the adder's input first is x, which is a. تمام. The other one is y, which comes from this multiplexer. This multiplexer has a select line coming in that from the comparator. The comparator compares this time 0, 1 with 0, 1, right? 0, 1 matches 0, 1. Yes, you get a 1 here. The 1 is passed to this multiplexer, right? So the output of this multiplexer is this input, right? Which is B inverted. B inverted is the 1's complement of B, okay? So here we get B complement. Adding A plus B complement, the 1's complement of B is what? A plus 1's complement.
A minus B.
A minus B, exactly. So what we get here is A minus B. This is logic. So the result is subtracting B from A. تمام? If you select 1, 0, 1, 0, then this is your input they're going to pass to the result. 1, 0 is adding A with B. Straightforward. 1, 1 is ORing A with B. A very simple multiplexer, ALU. Okay? Where do these signals come from? Why does 0, 1 come to here? If the instruction is 0, 0, 1, 0, 1, whatever, why do these two bits come to these two lines and these two bits to come to the A and etc.? Because the control unit is designed to, when it fetches the instruction, it decodes it, meaning separates the bits and sends them to the right signals. Who said there should be a signal here or a multiplexer here or whatever? This is the work of the architects, the architecture people, computer engineering architecture, okay? So it's not our business in this class. Okay, so this is the first component of the processor, which is the ALU. The second part is the control unit. The control unit's job is to bring the machine code, which is the program. Every program is converted to machine code and placed in the program memory of the microcontroller. So the control unit brings the machine code from the program memory, then decodes it, then passes it to the ALU to execute it. So here's the cycle. Fetch it from the program memory, then put it in a register, and there decode it, then execute it. Okay? This is how to do it. This is the basic, very simple functionality of the control unit. When it decodes it, it decides what goes to what line, what goes to on the address bus, what goes to the data bus, and so on. And it is related to the hardware design underneath. طيب. A machine instruction, a machine code, has several fields. يعني هذه machine instruction, add AB. طيب. Add AB, then you give it A, comma B. This is just an example. ماشي. This is converted to a group of zeros and one. 0, 1, 1, 0, 1, 1, 0, 1, whatever. And these are always constant, representing the add AB, because add AC is different, for example. Then, depending on these, you got some more zeros and ones, okay, to represent these operands. So this is all machine code. This is called the opcode field. This is mandatory. And sometimes you have operand fields related to operands that could be variable that you can change in your program, or the operands sometimes can be embedded part of the machine code. And we're going to get to that later when we talk about the addressing mode and the instructions mode. Anyways, so the instruction, every instruction execution depends on the signal clock, of the clock signal. Every controller, every computer, you say, okay, I have a 2.4 gigahertz computer. I have a 333 megahertz computer. What does that mean? This is the clock source that triggers all the logic circuits in that processor, okay? Today we're talking, we're in the gigahertz, right? In computers in general. But in the microcontrollers area, we are in general 8-bit and 16-bit microcontrollers, the most common ones. We're in the area from kilohertz to megahertz, usually in megahertz. For example, our microcontroller, the HCS12, we are able to configure it to work from, depending on the crystal. There is a crystal, 8 megahertz or 16 megahertz crystal. We're going to talk about it later. Okay. This is a crystal. Let me show you a crystal. if you see my camera, this is a crystal. It generates, we're going to talk about it. مثلا هاي مكتوب عليها written on it 8 megahertz. If you see it on my camera. طيب. A crystal, or they call it an oscillator, it generates a square wave. طيب, with a certain frequency. In our microcontroller, this signal that we get from the oscillator, we can process it in a clock block, okay? And we have a PLL circuit. We're going to cover it later. And we can multiply the frequency up to 48 megahertz. Okay, so we're going to be able to talk, generate up to 48 megahertz. In this microcontroller we're dealing with. Okay, who keeps track of the machine code that needs to be fetched? There is something called program counter. Program counter, short for PC, program counter. طيب. So program counter points to the address of the memory location with the instruction in the program memory that is going to be fetched by the control unit to be decoded, then executed. So it is like this. So I'm going to talk about this memory, the program memory. Okay. Okay. It's here. Okay. Okay. ماشي. Let me hide. ماشي. So we're talking about something called program memory. And the program memory here has several memory locations. The program memory here is a type of E² program called flash memory, okay? So it is non-volatile. What you write here stays here. So this is a program memory, for example, address 4000, 4001. What is the dollar sign? 4002. Hexadecimal number, right. So that's the dollar sign, 4003, and so on. So if you have a machine, an instruction called add A, comma B, and this translates into, for example, in hexadecimal to مثلا 3F2A, for example. This is stored here, depending on a convention called Big Endian or Little Endian. I'm going to talk about it later. طيب. Now, every location here برضو يعني can take, depending on a microcontroller. I'm talking generic. When we come to this one, we're gonna talk about how many locations every memory address can hold. So let's say it holds an 8-bit, every memory location, and we're using Little Endian. So the 2A will go here. ماشي. If this is Little Endian, if it's Big Endian, I'm going to talk about this later. This will be 3F. A fetch means that the program counter, first, when you reset your computer, the program counter there should be a mechanism that there is a circuit that will reset the program counter. What does reset the program counter mean? Reset, it means make it point to the first address where the first instruction, to the address of the first instruction of the program in the program memory. There should be a circuit that does that. A program counter, physically, what is it? It is a register. Okay. In some controllers, مثلا, in some computers, in PIC, they call it program counter or instruction pointer. In Intel 8086, they call it instruction pointer. In 8085, they used to call it program counter. Anyways, it is a register. Okay. A register. And its length is equals to the width of the address. Because it holds an address. The address. So in this case, if this is 4,000 hexadecimal, then it points here. It points here. So when the control unit fetches something, it checks the program counter register. 4,000. So I'm going to get the opcode stored at 4,000 and bring it to the instruction register. Okay. Then decode it. Okay. Then execute it. Okay. This is in general. Then what the program counter always increments. Then when it's fetched, the program counter will increment. The program counter will increment to point to the next instruction to be executed. So the first instruction was holding out, occupying these two first locations. The next instruction may come into these three locations, depending on its size. Okay, and this is different than RISC control microcontrollers like the PIC16, if anybody is familiar with that one. So that one, every instruction goes into one location. Here it varies. Anyways, then the program counter increments to point to the place where the next instruction to be executed. When the next fetch, when the first instruction is executed, the second instruction is fetched, then it is incremented to point to the next instruction to be executed, and so on. So what is the program counter? Program counter is a register that is controlled by some hardware. To what? To control the sequence of executing instructions, the sequence of getting, fetching, decoding, and executing instructions. So what controls the program execution sequence? The program counter. Okay, this underlying thing. The program counter, for short, it is PC. Program counter. It controls the sequence of executing instructions. Usually this sequence is sequential. It always increments sequentially to fetch the next instruction, then second instruction, then third instruction, then fourth instruction, and it keeps going incremental sequentially until it gets to a branching instruction. Okay, a branching instruction. Branching instructions could be conditional or could be unconditional branching. Unconditional, just do it, just go to here or jump to here, okay? Or branch if this is greater than this, or etc. Okay, and this instruction, the conditional or unconditional branching instruction, the result of it is controlling the value in the program counter. So in all cases, what the control unit fetches from the program memory is the instruction that is in the location where the program counter is pointing at in the program memory. How fast is the program counter moving? Depend on the clock signal. And on the clock signal, of course, and accordingly, every instruction, how long it takes to execute, also depends on the clock signal and on its nature, its length. Everything okay here? Trivial, huh? Third thing we're going to talk about. So we talked about arithmetic logic unit. We talked about control unit. Now I'm going to talk about registers here in the processor. And we talked about these two things, okay? Everything. So the registers is the only one thing missing. Registers, what are registers? They are storage locations, right? And last time in the last class, we talked about a register, right? It's a group of flip-flops. So a register is a storage location. Inside, usually, the registers are inside the CPU. However, their work could relate to the CPU or other stuff. So when we talk deeper about HCS12, we're going to see that there are CPU registers and there are port registers and I/O registers and peripheral registers, control registers, okay? But this is in general. The processor here, it has in it, inside the processor, some memory storage locations to hold the operand A and B when I want to add them, okay? So you can, sometimes you cannot add them while they are in the data memory. Sometimes you can, but anyways, usually data is fetched and put in registers. So the control unit, and this is governed by the hardware. So the ALU can act on them. So the ALU, for example, this is an ALU, just very generic. It always adds register A with register B. مثلا, it will output always stored in register A. For example, طيب, I have two different numbers in memory location X and Y. You have to bring them, put one of them, X put it in A and Y put it in B, then add them. Okay, so you have to put them in registers. This hardware only adds the contents of these two registers. You cannot, sometimes you cannot have it add anything just in general. You have to limit it to hardware. Anyways, this is the main purpose of registers. Some registers can or must have a register or more to perform an arithmetic or logic operation on it. And in this case, this register or these registers dedicated to perform operations on are called accumulator or accumulators. Some samples of such processors that do this, مثلا our HCS12, yes, has accumulators. PIC 18 family has accumulators. Intel 8051 controller has accumulators. Others don't. These مثلا processors have many general purpose registers that you can use any two to perform an addition, for example. It doesn't have to be A and B all the time. Okay. Okay, this is in general what's inside the CPU. So what we talked about, the CPU and its components, and the memory. Usually we have program memory. That is a type of E2PROM, which is a flash. And we have data memory. That is also is RAM and could have another E2PROM and I/O devices. Now we're comparing between microprocessor and microcontrollers. The very first people who were famous in microprocessors were Intel, but when they made the 4-bit microprocessor 4004, and that was in 1968. And I found this good table that compares a few processors. So let me tell you about Intel. Intel was their first 4-bit processor. 4-bit means it can operate on 4-bit numbers. It was in 1971, the 4004. Then later on, they made in 1972, they made an 8-bit version of it, and they called it 8008 in 72. In 1974, they added more peripherals that can do more things, more units, more logic into the processor, and created the 8080 processor. So we started with 4004. We started with the 4004. Then we got to the 8008 next year. Then in 2 years later, we got the 8080, also 8-bit, has more functionality. Then we got to the 8085. And this was also an 8-bit processor with more functionality. In 1978, we got the 80, they did the 8086. And this is a famous one. And many of you studied it at in undergrad. And the Pentiums today and most of the Intel-based microprocessors, this is its godfather, okay, or it's built on it and backward compatible. This was in 1978. This was the first 16-bit processor, 16-bit. Okay. طبعا in parallel with at that time they did an 88 processor, 8086 and 8088. When this was a big move from 8085 to 8086. They moved from 8-bit to 16-bit. At that time, the peripherals interfaces were not ready, 16-bit ready. So they made an intermediate version, the 8088, that works from its inside 16-bit, but it has 8-bit interfaces. طيب, in 1981, and this is not in the book, I don't see it, but in 1981, they made something called 186. Okay, 1981, yes, 186. That was basically an 8086 enhanced. طيب. In 1985, they made the 386. 386, but they stopped writing this 80, the 386. This was a 32-bit controller, processor, sorry. Then in 93, and I still remember that day, they got the Pentium, they produced the Pentium. The Pentium was also 32-bit. When they produced the Pentium, they produced several versions. In 95, they did the Pentium Pro. And I remember in 90, I think 97, they did the Pentium MMX. Then they did, in 98 maybe, or something, the Pentium 2. 99, they did Pentium 3. And up to the Pentium 3, everything was 32-bit. Okay, then they moved to the Pentium 4, then they started producing other kinds of, the Pentium is built above the 8086, but they have the Itanium processor, and other architectures I forgot about, honestly, but the Itanium was 16-bit. That was in 2001. Other companies were also working in parallel on producing processors or controllers, but Intel was the lead, honestly. Motorola produced the 68,000, or sometimes they call it the 68K, the processor, Motorola. Okay, this was 16-bit processor, 68K, in 1979, sorry. So it was almost around the time when the 8086 was produced. Okay, so they both competed. Motorola later on, the division that continued to produce microprocessors, okay, the 68K is the predecessor of the HCS11. There was an HCS12, 11, HC12, then HCS12, the star version of HC, okay, then and the MPC and so on. They went more into microcontrollers, and they were became a very the microcontrollers semiconductor division of Motorola spinned out as a new company, and they called it Freescale. So when we look at the data sheets later on, we're going to see Motorola's name on some of the data sheets, then Freescale on some other data sheets. Today, it's not Motorola nor Freescale. It is an XP. Okay, Microchip has a history as well. they're most famous in microcontrollers rather than processors. The processors are much simpler. So a CPU looks like this. This is a history. It doesn't have inside it. So when we talk about this Pentium 4, we're talking about this piece. It doesn't have the RAM, the program memory, the I/O peripherals inside it. No, they're not inside. You have to interface with them through the buses, okay? Because it is general purpose, and what you interface with is what you need. So you don't have inside it any analog digital converter, D to A's, A to D's, parallel IOs, memory, nothing, okay? You don't have those. It's a processor. But it's a very high performer. It has a very high performance. You have flexibility to interface it to whatever you want. It is expensive, power consuming, gets a lot of heat, and it has a big size, honestly. So أنا هذيك اليوم I was searching around in my old stuff, and I found this. If you see it, a Pentium 2 flipped. I don't know why the camera is flipped, but this is a Pentium 2 processor. See my hand. طبعا if you remove this heat sink, well, you can see it. I don't want to remove it. This is it. This piece is the microprocessor package. Okay, the Pentium 2. This is the Pentium 2. And at that time, I don't know, is this the price? No, by Intel. Anyways, and the other part, this one, a fan with a very large heatsink. And I never remember that I ever got a processor that is less than $150 or something, or at least 110, 120 JDs. If you compare this with this is a microcontroller, see? This is a board. I'm gonna remove this breadboard, okay, to show you the microcontroller. This is the microcontroller, and this is the microprocessor. See, this controller, inside it you have program memory, data memory, A to D, D to A, serial communication. This chip, okay? The board is for us to make our life easier because we are developers right now. It's not industry. But this is a CPU. See, huge difference in size, thus cost, and heat dissipation. It has advantages, but you don't need all this processing power in all of your applications, especially in things that need to be smart. A small brain can make things work. So a small processor with some extra abilities can do it. So a microcontroller, this brings us to the microcontroller. A microcontroller is a processor along with all the things, the memory, the I/O interfaces on a single chip. You got your microcontroller. So typical stuff you have inside a microcontroller is the memory with its two main types, the program memory and data memory. You have a lot of timer functions. Timer functions are very important to do real-time systems, to build operating systems, to build PWM interfaces. Honestly, for me, in the old time, when they talk about timer functions, I always think of it, look at it down, and okay, good, I can do some good timing. But timing it could be the most important peripheral here in this microcontroller. I'm going to spend some time here. Without the timer functions, you're not going to able to operate motors, for example. You're not going to be able to operate DC motors. You're not going to be able to create interrupts. And accordingly, you're not going to be able to make an operating system and so on. It has serial communication interfaces, a typical microcontroller that ranges from asynchronous communication to synchronous communication to networking, either with the internet or with other kinds of controllers. Analog to digital converters that can read analog sensors, digital to analog converters to produce analog signals, DMA to directly access memory, parallel I/O ports, that is initial, that is basic, must, and has to be there in almost every microcontroller. You cannot interface a simple push button without a parallel I/O pin. Memory component interfaces for extra memory, such software debugging to support inside the chip itself. You have supporting software to be able to single step it and debug it and so on. So it is usually low cost. Yani this microcontroller I have here, I have a controller here. يعني ماشي كيف بدي أشيله هذا. Well, you know, يعني this is a simple controller. بدريش قديش حقول اردوينو اليوم بس. The pick, this one is a pick I have here, 2-3 JDs. I don't know, with Jumrook and everything. This one, I didn't buy a chip by itself, but the whole board is cheaper than that processor. See, so usually low cost, low power consumption, lightweight, has everything you need, standalone. With this, I can fly an airplane. ماشي. Any questions so far? You guys are, I don't know, tricky. You keep me speaking and are you with me?
يس دكتور.
دكتور كله واضح.
واضح؟ متابعين معي؟
تمام يعطيك العافية.
مستمتعين ولا نعسانين؟
لا مستمتعين طبعا.
Okay, a lot of stuff. Watchdog timers, UARTs, PWM, and I'm sure a lot of these terms are new to many of you. But with time, while we go, I'm going to be explaining things. Okay. To show you a simple application on dimming a light, a simple light, using a processor in case number 1 and using a microcontroller in case number 2. First, you have to have code, right? I have a light here. This is a light, and this is a light sensor, that detects the light intensity around you. So if it's dark, you turn on the light brighter, and so on. طيب. So it's a photoresistor usually.
LDR دكتور.
عفوا.
LDR اللي هو.
Yeah, it could be an LDR, yes. Light detecting resistor or dependent resistor. Okay, so to build this application using a microprocessor, first you have to have your program in the program memory. Let's say here in the program memory. It has to be written, and it should know the addresses where everything is located. So you should know that there is an LDR or a light sensor located at address X, and this is I/O. What do they call it? Memory address I/O. Memory address I/O. So okay, you need to go read the data on the from the data bus at this address to select this data at this read by this analog digital converter external. Okay, so you read the instruction from the read sensor instruction from the address. So the address bus puts the address of the first instruction, loads it to here, to data memory, brings it to the processor, decodes it, understands that I need to read a sensor at address X. Then you write address X on the address bus. Okay, you select it, you read the data here, bring it. You do your if the reading was greater than X or Y or whatever, then you decide, oh, I want to dim the light or turn more the light or whatever, you need to send a signal. Okay. And all these Fs are signals in the program memory or instructions in the program memory. So you're going back and forth here a few times. Then, okay, turn on the light. You need to go to turn on the light is an instruction. You bring, decode, then you understand, then you execute, and then you need to turn it on. You need to write a signal on the data bus, مثلا 1, and select the address where this is located, depending what the address is. Then you write the one will cause a channel here, and with let the light turn on. Not easy in terms of hardware and even writing the code. Comparing this to this simple thing, a microcontroller. If you use a microcontroller, you have a general purpose I/O, a parallel port we call it, okay, and an analog to digital converter inside already. You don't need to worry about its details here. You connect the LDR to it, okay. You say read A to D. والله يعني دي جد هيك we're gonna do it. Read A to D. If and put it in X. If X greater than مثلا threshold threshold تقدر تغيره يعني okay on function مثلا أو off else off. طيب on يعني شو on هاي بتكون on يعني روح حط go to pin number 1 إذا هذا pin number 1 in port in port يعني we're going to see how to act to يعني deal with ports. In port B مثلا write a 1. You write a 1 N channel. You let the current pass through the light. You turn it on. If you write a 0, no channel here, no current passing through, the light is off. As simple as that. So this is a microcontroller, and this is how it's different than a microprocessor, its benefits. And now we're going to start talking about our microcontroller. Any questions so far? No questions.
So far, so good.
So far, so good. Great. طيب. Next. Now we're going to talk about, I told you, in this class, we're going to use 2 microcontrollers. One, to help us understand what is a microcontroller, what's inside it, what are peripherals, okay, how to use them with very low-level detail and worrying about the register level, the hardware level. We're going to be talking with the hardware, very low level. طيب. This is the HCS12. And second is the other microcontroller, the Arduino. We're going to use it to demonstrate embedded software design. Okay? In the HCS12, we're going to use it to do conventional software, embedded software design. We design our things using conventional tools, then we write our code. طيب. The model-based part, model-based hardware, embedded software, we're going to do it on the Arduino. Why? Because it's cheaper, basically. And in model-based, you don't care about the details of the underneath hardware. You just use models, blocks, and you let the IDE you use to autocode generate the thing you want. So it doesn't matter. It will be the same. But it is important to talk about this microcontroller, the HCS12. We call it HCS12 microcontroller. To understand a lot of important concepts. Okay, so the HCS12 microcontroller. Before I start, we're gonna start seeing things here. Before I start with the details, the HCS12 microcontroller has many family members. طيب. Many family members. This is its name. The family member we're using here is this one. It is called MC microcontroller. S is for the star family, 9 star, I think. 12, HCS12, because there was something before called 11. DP, these two letters stand for the type of the controller. في DP, في DG, في شيء, there are some stuff medical grade, there are some stuff military grade, commercial grade, you know. So we're going to use the DP or DG, they're very close. And 256 is the flash memory size. This is the flash memory size. Flash memory. What is flash memory? You know, anytime now, I'm going to use the two words interchanging them. What does flash memory mean?
البروجرام memory.
Program memory. خلاص. Okay. Program memory. So this is the size of a program you can have. 256K kilobytes. Okay. Great. Now this family member has a data sheet, a standalone, and I'm going to show it to you. So if you go to the e-learning, I have uploaded refresh. This is, I have uploaded here the MC912 DP256 datasheet. Okay, so if you open it, this is it. 256 DP, advanced information, family number, December 2000, Motorola. See Motorola's name on it still. And they did it at Motorola time before Freescale. Motorola then became Freescale. Now it's an XP, as I said. And this is its content. And this is very important. Listen to this here. Everything we're going to need about this microcontroller. And this is a general rule for any microcontroller you're going to use ever. All what you have here, see the write-up here, the size, the features. Then later on, we're going to come to see any, and I have a slide here. I have a slide about the schematic or the block diagram, sorry, of the controller. The original comes from here, comes from the data sheet, okay, with all the details, okay, very high resolution. Then you come to more even details. The first thing, the CPU, the addressing mode, see? Opcodes, the program model, data type, everything, okay? Everything, see, registers. We're going to talk about all of these things. You're going to see them in my slides. They're going to be in the book. But let me show you just a very simple thing. Yeah, these are the instructions, how they operate on the operands, what is the addressing mode used, the machine code generated, what are the flags that are affected, okay? All the details about the CPU. Then you come to the peripherals one by one. And just quick, one by one, just I'm gonna open one of them. Port A, the ports, these are the parallel ports. Something easier, the interrupt and reset vector. What else? I'm gonna find something easier for you guys. Mapping the resources, all addresses, all registers, memory maps. I don't know, what is this? The civil control. And show all the details, we're still here. If you go to something else, what is this? The PLL clock, I2C. What else do we have? I2C. CAN bus. Pages. 500 pages. Scan. Anyways, I don't want to go a lot there, but what I want to show here, and this applies to any microcontroller, what people, when they go do these books, when they write these educational books, everything inside, yani, look at this one. What is this? Timer function. What is this? I don't know if you see these things, but yani, the registers, the comment, yani, everything about the details, what every bit does. Okay. ماشي. قبل شوي شفنا الاي سكوير سي analog to digital converter. These يعني أنا هون بدي I'm gonna go to the analog to digital converter. Where is the I square C, I square C, CRG, pulse width modulation. يعني أنا إجا عندي هناك أسهل. SCI. طيب SCI overview, serial communication interface, everything here. If you go to the chapter of SCI, I think it is chapter 9, yes, here. And they give you an introduction, theoretical background, okay? But eventually the circuits, the registers, everything is taken from the data sheet, okay? So what I want to say, the data sheet is our main reference for everything. It's more accurate, and sometimes if you, if it's not more, it should be the same. But it has a lot of more details, very low level, about whatever you need about anything regarding the controller, okay? And it's always the reference, because things depend on how they were designed, their hardware and everything. So our reference is the data sheet. Okay. So at a higher level block level, the HCS12 microcontroller, this family, we're going to use the DP256, is a 16-bit microcontroller. What does 16-bit mean? It means that the internal registers, the internal data paths inside the microcontroller are 16-bit. You can move 16-bit at once, not 8, but then another 8, 16 at once. طيب. It uses an HCS12 CPU, a processor. This is inside a single chip. The كله single chip. It has an internal bus to move things around between the peripherals. First thing, other than the CPU, we start with the memory. The main memory, the biggest memory is the flash memory, the program memory. This is the program memory. This is where we write our code. طيب. Then it has an address space. We talk about it later. Then we have the data memory. This is the data memory, data. But it's two parts. The RAM part, 12K, that is a volatile memory. You store in it temporary data, and 4K, 4 kilobytes for E² PROM. طيب. Non-volatile data memory. We have two A to D peripherals. Each is 8 channels, configurable to 10 bits. I'm going to talk about the details. What are these numbers? What is a channel? What is the 10-bit resolution? And so on. It has 8 channel. It has a timer, enhanced capture timer, we call it, to do input capture and output compare. I'm going to talk about that later again. 8 channels that are 16-bit each. It has PWM unit peripheral that could be configured as 8 channels, 8-bit each, or 4 channels, 16-bit each. This is a very important feature. Okay. It has 2 SCI, serial communication interfaces, asynchronous communication. and it has 3 SPI, serial peripheral interfaces, synchronous communication, and 1 I2C synchronous serial communication peripheral. In addition to voltage regulators, interrupts and wake up IRQ ports and circuitry. It has 5 CAN buses, bus peripherals. You can do 5 networks. Okay. CAN stands for Controller Area Network, the LAN, Local Area Network. This is different than serial communication. Serial communication, you use it usually for one-to-one communication to make this microcontroller talk with this microcontroller one-to-one, okay, or this controller talk with my PC one-to-one, okay. But if I want 100 controllers talk all to each other like a network, you need a CAN, مثلا CAN network.
دكتور الكان بس بيفرق كثير عن الكان اوبن ولا نفس الشيء وهذا فاميلي من هذا ولا كبروتوكول؟
الكان اوبن شو هذا everything الكانو كان open can many versions many industries try to do their own, but the CAN standard is the same. The CAN standard is the same because it's a de facto. They call it the de facto. يعني it is an industry standard that يعني I'm going to talk about it, but that is just there in the industry. It has its standard and people just use it. They consortiums were created to try to make a better controller-based networking system that has more capability, faster, and blah blah blah. But those did not work. They did not work. Like the FlexRay. FlexRay, for example, is a network protocol. If you want to compare the CAN can range its speed up to 1 meg and 2 meg bits per second, and it can go to its bus can go up to 130 meters, actually, with up to 100 controllers communicating all with each other, message-based, different. A consortium was created between the big automotive industry companies, and they created a network protocol and system standard called FlexRay. FlexRay. تخيلوا هذا قديش FlexRay. The FlexRay was they first used it in the BMW, سيارة BMW, what is that SUV? X5, VX5, I think, X5. In the BMW, it can go up to 10 megabits per second. Okay, addressable وفي timing فيها more accurate, which means يعني you can guarantee a delivery time for a message different than the CAN. They use it in the suspension system, and it's hydraulic suspension system. The شو يعني suspension system? نظام التعليق snowball sat. So it can keep going smoothly, and the controller control when it goes on rough road or pumps and bumps and everything very fast. And then it was never used afterwards. It didn't work. The CAN خلاص يعني de facto everybody's using CAN, just continue using CAN, and CAN is there. Okay, it has many security issues. Today the data on the CAN bus is still in raw data. So that's why a few years ago they hacked a Jeep Cherokee on the highway. Somebody was able to get the message ID of the brake. We're talking about brake by wire. He plugged into the OBD where you have the 2 CAN bus lines, and made a microcontroller to write a signal with the same ID of the brake message ID, wrote it in a faster pace, overwrite the original signal of the brake, and cause the brake to hit, and what is it? The car to stop on the highway. And let's make use of being doing things remotely. So it was on CNN, Jeep, and Cherokee, how do you write Cherokee بالسي صح؟ Stop on highway. Jeep Cherokee, CNN Cherokee Nation asked Jeep to stop using. This is 2021. Okay, oh man, no, this is something new. 2015, hackers. Jeep remotely carjacked, shut down on highway. They stopped it. And they killed the engine. Jeep is a part of Chrysler, where I used to work at. And yeah, this is something. Hackers can cut the brakes, shut down the engine, drive it off the road, or make it flip. And I'm always telling the people, be careful. The coming future hijackers of planes, of cars, they can do anything if they have access to your CAN network by plugging something. It's two wires. This is this controller. Let me show you where is the CAN interfaces. The CAN interfaces. Where's the CAN chip? I showed you the chip last time. Here it is. Here, see, there is something called here CAN high and CAN low. I don't know if you see it. يعني هي CAN high, CAN low. هذول البرقيين الاثنين. Underneath is the CAN transceiver that just strengthens the signal. Okay, I can write code. When you end the class, you are going to be able to write code to write any CAN signal. And if you can take these two lines, that's silkain, connect them to the two lines of your OBD connector, which connects them to the CAN network. Then it's your call. If you are able to experiment, hack, sniff, you can sniff all the signals and try. When I hit the brake, what's going to happen? Just plot it. When I hit the gas, what's going to happen? Plot it. And then discover what signal is for what, and you can just go hack it. Hardware security. And until this moment, they do not, it is written on the bus as raw data. Raw data, what does that mean? You sniff text. Yes.
encryption.
It's not encrypted. They cannot encrypt it because it will violate real-time constraints. Yeah, يعني it is decrypting is gonna take time. Anyways, inshallah we'll talk more about this. But I don't know what a question just popped up about CAN. This is CAN. طيب. We'll be talking more about what every one of these things mean. And you know, when we talk, why am I doing this? Because I'm not going to be able to find a CAN on an Arduino. I have to buy a shield, and you just use it with those libraries. You don't understand what's going underneath. More to hobbyists, you know. That's why we need a very powerful, good one like this controller. طيب. These are more details, but I'll show them on the, and you go look at them in the data sheet. Now you have access to the data sheet. See, you have 256 kilobytes of flash E2 This can vary from a model to another. 12 kilobytes of RAM. RAM is the data where when you say integer X, you go book a place for it in the RAM, okay? This is the program memory we said, and this is the 4K byte E2 another data memory, okay, but for non-volatile memory. Voltage regulators to generate voltage signals and regulate them. The CPU, see inside it, you have a PLL circuit. There is a complete full chapter about this, okay? And this feeds the clock signals to all the circuitry, the blocks, the CPU, and everything. And part of it is the periodic interrupt, because it needs a clock. A COP is, what does COP mean here? COP is the watchdog timer. The more common word is the watchdog timer. It's 6:15. I think I need to stop. We'll continue later on the details. Most of the things here have a chapter covering them. This first part, okay. You know, this first part, just to close the things, embedded computers, we talked about it. They're everywhere in everything. This talks more about memory technologies, magnetic, optical, whatever. You go skim through them. We talked about RAM, E2 PROM, flash. Okay, yani let's say we stop at computer software and talk more about computer software next time and how to start programming the controller. I have to end here and see you next week, inshallah.
دكتور يعطيك العافية.
If you have questions, please stay and ask whatever you want. Thank you.